Hi, this is Robert Quimby, and I'm going to tell you about least squares fitting with a shift. So in this video, we're going to quickly review how you can do least squares fitting in Python, specifically how you can fit a line to some data. We're going to discuss the uncertainty in the best fit model parameters and how that extends to the values that you predict from your model. And then we're going to see that that model uncertainty can actually be minimized with the right choice of coordinates. And the short answer here is that if you have some distribution of data, you want to do your least squares fitting on a coordinate system that is centered on those data. That can often be the best choice. Alright, so to get started, we're going to load some data into Python, and we're going to use NumPy's gen from text, and we're going to load the xy.dat file in the media folder. I'll just load this in. We're going to take a look at what these data are. We've worked with this before, but just to remind you, we'll plot it up. So we're going to use matplotlib. We're going to do inline. We're going to set up the plotting and make the plots a little bit bigger than default. Okay. So now we can go ahead and make a scatter plot of these data. So I can use matplotlib scatter function, and I'll pass it the data x values and the data y values. And let's plot this in the color red. So C equals R. Okay, C equals R for color equals red. So if I run this, there we go. There's our data. And I've added some kind of bare minimum axis labels here where we didn't specify what we have or what units, but we're just going to call this the x value and this the y value. And you can see we have some distribution of points. And if you're an astronomer, you can look at this and you can say, you know, I can fit a line through there. So let's go ahead and do that. So how do we fit a line? Well, first thing you have to do when you fit any model to data is you have to write down what your model is. So in this case, we're going to be fitting y equals mx plus b. So this is the form of the equation. You need to write that down. And then we can notice that we can take this system of equations. So we might have actually a whole bunch of observations. So if I go back, each one of these data points must obey this relationship here. So we actually have a system of equations. And when you have a system of equations, it can be helpful to put them into matrix form. So that's what we've done here. We've made a column matrix with all of our y values, and then a two-column matrix with our x values, and then the number 1 here. And then we have this third matrix here that has our parameters that we want to fit for, m and b. And of course, if you take x1 and multiply it by m, and take 1 and multiply by b, that's gets you y1. So this shows you that we've just taken all these equations we had and we can represent them in the same form mathematically, but in a matrix for convenience. All right, so this is the math. Now how do we do that in NumPy? Well, we want to make a matrix, so we're going to use NumPy matrix. And we're going to make a list of lists because we want a column matrix. So we're going to start with our X matrix here. So the X matrix, as you may recall, has 2 columns in it. The first has the X value and the second has the number 1. So we are going to have our ith X value and the number 1 in each column. So we need a list of lists here. So we need these extra parentheses here. So we're going to do, the list is going to have this for each xi in our data x value specifically. So we're using list comprehension here to make a list of lists with those values. Now we're going to do the same thing for our y matrix. We're going to have a list of lists with each yi value into a single column matrix, so we don't need anything else there, for each yi in our data of y. And then of course to solve this we have to do a little bit of matrix algebra, but it's pretty straightforward to do, and it solves out to we have y on one side of the equation, we can multiply that on the left by x transpose, and then we can multiply that by our covariance matrix, x transpose times x all inverted. So if we multiply that out and run this, that'll solve for our best fit parameters p in the least square sense. So now we know what m and b is. So we can plot this line now. So we'll do a scatter plot just like we did before. We will label our axes, and now we want to plot the line on top of that. So the way we can do this is we got to plot x versus y. We have this matrix X that has all of our x values conveniently stored in it, but they're stored in, there's two columns, and we don't need both. We just need the first. So we can tell it, we can take all the rows, and we'll just use the 0th column, the first column. So those are our x values, and then our y values, we can calculate the y for all of those x values just by taking our x and multiplying it by our p matrix. And if we run this, there we have our data, now with the best fit line shown. So now we want to address what the uncertainty is in this fit, this model. So we'll start by calculating the parameter uncertainties. So the way we do this is we, of course, define our best fit model using our best fit parameters. So that's our model values. We subtract that model off of the actual data. We get this delta matrix. We count how many data points we have and how many model parameters we have, and then we can calculate the sample variance. There's different ways to do this. This is just one way using matrices. And then we can calculate the parameter variance just by multiplying the sample variance by the diagonal terms in the covariance matrix. And we'll take the square root of that to get the sigma, the uncertainty in the model parameters. So the best fit parameters are stored in P. We can break these out into M and B like so, just using this, taking our matrix and converting it into a one-dimensional array. And we can do the same thing with our best fit model parameters, because this is also a matrix. We'll take it, convert it into an array, one-dimensional, and pull out the M and B sigma values. So then we can actually go ahead and calculate. I'm doing the same thing. We don't need this. We can do the same thing, and we can print this out. That's all we're going to do here. Okay. So our best fit M is 455 plus or minus 62.92. Remember this number. We're going to see this in a little bit. And for the y-intercept, we get 12.77 plus or minus 69.78. So remember this again. We have uncertainty of 62 in M and uncertainty of about 69 in B. All right, so now what I want to do is actually give you a graphical representation of what this uncertainty corresponds to. So what we're going to do is we're going to plot some models, and we're going to use the uncertainties we just calculated to make a random selection of models that are consistent with those model parameter uncertainties. So we're going to start off with the slope parameter M, and I just want to create a bunch of random values that are consistent with the best fit value we have in its uncertainty. So I'm going to use NumPy random to get these random values. And there's different types of random numbers, and we want the normal distribution. And this is another word for a Gaussian distribution. And we want that distribution centered at our best fit value M, and we're going to give it a width, a standard deviation of m sig. That's our uncertainty. And we're going to have n data points, where n is specified in this function here as defaulting to 30. All right, so that's for our slope. For our y offset b, we can do the same thing, except for instead of centering the distribution at m, we'll center it at our best fit b and use the b standard deviation. So then what we're going to do is we're going to create a bunch of lines. We're going to plot a bunch of lines. So we'll plot the data, we'll plot our best fit model, and then we'll plot a whole bunch of model lines using each one of these randomly chosen slopes and offsets. And we'll just see what that looks like. So we'll run this function here. We'll run that cell, and then we can run the function. So we'll take our plot models function we just defined. We're going to pass it the data, our best fit M and B, and those uncertainties. And we can run this. and that's what we get. So there's again our data points, and we have the blue line as our best fit, and then the gray lines here, those are just a random sample of models that are all consistent with our uncertainties. Now if you look at this, you might see something interesting. And by the way, your plot might look slightly different because these are randomly chosen m's and b's, so these slopes all will be different. Every time I run this cell, I'll actually get a slightly different version of this plot. So you might have slightly different version than I do. But what you might notice as you look through a bunch of these is that there's something unsatisfactory about how these fits look. You notice that the y scatter here looks huge, and it doesn't seem really to follow the distribution of the data points around this best fit line. It seems like the scatter is too much. And you also notice that, if I can find a good one here, the first one was actually pretty good. You'll actually notice that the distribution is wide on this end here. It's a little bit wide on this one, and it comes to a minimum. I'm just looking at the vertical extent of these models. It comes to a minimum around a value of 0 on our x-coordinate. And that actually has to do with how we fit the data. All right. So we're fitting with this as the origin, and we're basically asking it to tell us what the y-intercept is, and we're fitting for that parameter. And if there's any uncertainty in this offset, and there is, that gets translated all the way across here, but it's actually magnified by the slope. So the farther away you move from this intercept point here, the greater that uncertainty is going to end up being. So it gets magnified. So that's not ideal. What we want is a best fit line and its uncertainty that best represents these data, so we can say, hey, what's the value going to be at an x value of 1 or an x value of 1.5, and we want the uncertainty in the model predictions to be as small as they can be at that point. So we can do this, and the solution is to use a shifted origin. So what we can do is, instead of fitting y equals mx plus b, we can do a simple change of coordinates. So we're still effectively doing y equals mx plus b, but we're just subtracting off a y value from our y's and some central x value from our x's. And so we're effectively just shifting the origin that we're fitting for, but otherwise it's the same fit. But this has an advantage that we'll see shortly. So we can do this. So what we need to do is we need to pick a central xy, x0, y0 coordinate. And a good selection for that is actually just use the mean of your data. So if we go back to this plot here, instead of putting the origin over here, right, and all of our data are to the left and above that origin right there, why don't we put the origin in the middle of our data, somewhere around here, right? So the way we can select that is we can just take the mean value of all of our x data points, and we'll call that our x coordinate center, cx. And then for cy, the y-coordinate center, we'll just use the mean of the y values. Right? So now we can rebuild our x matrices, x, y, and matrices, and we can do our fit again. So we're going to do the same sort of format we did before, but instead of just using our ith x value, we're going to use the ith x value minus our cx. This I'm using slightly different notation here. So cx is this offset x0. So we can fit for that. And same thing here, our ith y value minus cy, our central y value, or y naught if you prefer. You can write it either way. It's just a variable. So we can run this now, and we'll get a different best fit parameters. So what does this look like? Oops. Well, first we're going to calculate the uncertainty now. So we looked at the uncertainty before in M and B. Now we're going to see what the uncertainty in M and B is after we do this change of origin for our coordinates. So same as before, we're going to predict our model values. We're going to subtract off the actual, subtract those predictions off of the actual data to get our delta y. We're going to calculate the variance for the sample. We're going to get our best fit parameters. I'm doing this a little bit different than last time, but it's effectively the same thing. Just give you a little variation in how you can code this up. And we'll get the uncertainty in our parameters using our covariance matrix and the uncertainty that we got from our sample. And then we can go ahead and plot print these out. And I'm going to call these M2 and B2, MSig2 and BSig2, just to differentiate between the values we calculated before. If we run this, we see that M2 is 455.71 with an uncertainty of 62.9. I'm putting the wrong thing here, aren't I? Yes, I'm printing the wrong thing. I'm sorry. I wanted to print MSig2 and BSig2. I'm sorry about that. So if I run this again, you'll see the uncertainty in M actually doesn't change. So the slope, you get the same exact slope we got before and the same uncertainty as before. Nothing changes in the slope. However, for the offset, there's a big change. First of all, the best fit offset now is 0 because that's how we've organized our coordinate system. Actually, we'll see this later. But more importantly, the uncertainty is much less. Remember, before the uncertainty in B was 69, and we just saw that when I plotted it, printed it incorrectly. But now it's dropped considerably, so we've got much less scatter. So now we can go ahead and actually plot this up. So we're going to use a new plot models 2, and it's going to be very much like it was before, except for we're going to account for this change of origin. So it's going to be passed as keyword parameters. We're going to plot our model minus. We're going to plot those gray lines for our model again. And by the way, this color, this is how you make it a shade of gray. So if you set the color to a string, which is actually representing a floating point number between 0 and 1, it's going to give you a gray shade between black and white. So 75% is mostly white, so it's a little bit on the light side of gray. All right, so we can run this, and then we can plot our data. So we're going to again plot our data and all of our model parameters centered at a specific origin. And this is what we get. And if you look at this, now you can see that this is actually kind of qualitatively different than what we saw before. Instead of having all the gray lines pinched together at x equals 0, they're now pinched together here at the center of this distribution. And what that means is our uncertainty in our best fit model is actually much lower where we have the data points than it was before. It still blows up on the sides. You can't avoid that. We don't have data out here to constrain that, so that makes sense that the uncertainty would be larger out here. But where we do have the data, you can see that we do have now the best constraints on our complete model. So last thing is we can just directly compare the slope and offset that we calculated in the original system and in the shifted coordinate system. I'll just run this. And you can see again, we get the same slope, same uncertainty. Our B value changes, and the uncertainty in that changes, and that's why we now have these lines, these model lines, which are tighter in the center of this distribution here. But it's important to note that we haven't actually changed anything. We can actually recover the B value from our original fit just by figuring out what the our shifted origin model predicts at x equals 0. And it should be the same, and it is. We still get the same value, so our y-intercept at x equals 0 is the same as it was before. That doesn't change. And actually the uncertainty doesn't change too. All that changes is that in these other data points, when you move away from that origin, now the uncertainty is dropped. So this is handy to keep in mind when you're doing least squares fit. It's worth spending a little bit of time and considering the form of your model and where you should put that origin. So play around with this and enjoy.